Today we're going to be learning about sets and some symbols we use in mathematics. The first question we must ask is, what is a set? Well, a set can be thought of as a gathering of stuff or things that is put in a group. This stuff or things are known as elements. And so this is how our symbol for elements looks like. And what I just said right now, that's our stuff or things. So you could think of elements as stuff or things. Do you have any ideas of things that are sets? Well, we could have a set of cards, or a deck of cards, I should say, that has 52 elements within it, or 52 cards. So if you have a deck of cards, it always comes with 52 cards. And those you could think of as your elements. So here's another example. A normal adult has a set of 32 teeth, each individual tooth being an element of that set of teeth, which means we have 32 elements within our set. And so these are just some examples of how you could visualize what a set is in mathematics. So now the second question we should ask is, what does it mean to be a language of a set? Well, we will define both the literal and the figurative sense of this question. So first, let's define the literal sense of this question. Well, we can say it follows symbolically the language of sets, or linguistics of sets. And so all that really means is that sets have their own language. And so I already showed you one of the things that sets use all the time. This symbol, you remember what I said, take note? It means elements. We use brackets, and we use ellipses. So that's what this means. It means and so forth. And so I could go on with a couple symbols we use for sets. But let's define the figurative sense of this. And figuratively, we can say that for whomever or whatever our sets are, they must follow the logical consistency of being an element to a given set. And so we should take note that both these definitions define a set in its own manner. Now that we have passed this threshold of this thought, let us begin with some notations that are crucial for writing sets. Alright, if S is a set, the notation X is an element of S means that X is an element of S. Alright, so this is the first part right here, what this is saying. So let's address this. And if you're taking notes, make sure you have this down. So it's first we gotta address what kind of statement this is. And if you saw my first video, you know this is a conditional statement because it says if, and this comma represents a pause for a then. So if S is a set, X is an element of S. And so I made sure to color code this so you guys could see the following. X is an element, so this is what this means. X is an element of S. So that's what this first one means. So let's do this next one right here though. And so I want to make sure I put little stars or things, whatever these are, right next to the most important things you should take down as notes. This next one says X is not an element of S. So that's all it's saying. So X is not an, which is in blue, element, which is in a lighter blue, of S, which is in pink. So you guys can clearly see what and follow what I'm saying, my train of thought. And so this next one says set roster notation. And so what does that mean? Set roster notation. All this means, don't care about the elements in here. Forget that there's elements in here. So this one's pretty important too. It's saying the notation we use, the brackets. So pay attention with this one. Set roster notation. If they say put it in set roster notation, we're going to put it in brackets. So this next one says the set of all. So what is this statement? It's a universal statement, remember? That's why in chapter 1 we learn our statements, because in math we use those statements all the time. And there I said a universal statement myself. So here, set of all integers, the integers are within this, our brackets, set roster notation, from 1 to 100. And so you could clearly see that this is all positive integers from 1 through 100. But this is not that important, so I'm going to put an X on it. Just something to take note. So this next one says set of all positive integers, and so on, and so forth. So you can read it both ways. Formally is and so forth. And so this one's more important, but it's pretty much common sense. So I'm not going to ask you guys to memorize that, because you wouldn't need to. It's just pretty much common sense. So the last one has little 3 dots, and this one's really important too. We just used it in this top one, our top symbol. So let's see. This is our ellipsis, ellipsis. So that's what it's called. Kind of like when we had those ovals in calculus, ellipsis, right? And all it's saying is and so forth. So 4 things to take out of this. These 3, this last one, and if you remember the one I told you to remember, the elements. And we could take this one too. That means it's not an element. So that's 6 things to remember right now. So keep that in mind. Alright, and so I just want to mention one last thing so you guys don't get confused. So ellipsis, they're saying the same exact way as this. They have the same pronunciation. So they're pronounced the same, in English at least. But they're spelled different. So this is ellipsis, 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 because with the E. Ellipsis with the I, because the E and I, they're making the same sound. So keep that in mind. They're not spelled the same, but they sound the same. So what does axiom mean? So you might have heard this term in math, or you might haven't heard about it yet. And axiom is really important, and we use axioms in math all the time. The problem is people don't know what it means, and so I'm going to tell you what it means right now. An axiom is a true statement for the starting point of our ideas. And so what does that mean? True statement. Let me write it up for you guys. So you could be like, oh, okay, you finally understand what an axiom is. It's a true statement. So what does it mean to be a true statement? We learn about statements in our first chapter. And so all it means is that whatever the statement is saying is true. The statement has to be true. It's not false. If it's false, it's not an axiom. If it's true, it's an axiom. And then it says an axiom is a true statement for the starting point of our ideas. And what is it? The starting of ideas. So there's 2 things to get out of what an axiom is. It's a true statement, and it's a starting point for ideas. And so what does it mean to be a starting point for ideas? Well, if you know anything about math, you know that, and especially if you're taking this course, you probably learn about some proofs and stuff. You know that everything in math is based off ideas. And so that's all an axiom is. It's ideas. So this is the most fundamental things in math, the proofs, right? When you're learning about proofs, all they are true statements, and they're the starting point of ideas. So a lot of true statements build up our proofs, right? If our statement was false, then our proof is false. And so that's all an axiom is. It's the building blocks of mathematics. That's the way you could think about it. And you can also think about it, it's a true statement, and it's a starting point for our ideas. So if we're to write out a proof, we got to use axioms in order for us to justify what our proof is. The axiom of extension says that a set is completely determined by what its elements are. And so what does that mean to have its elements? So we just learned earlier that this symbol means elements, and we also learned some examples of what being an element is. So let's keep reading on. It says, not the order in which they might be listed, or the fact that some elements might be listed more than once. Alright, so let's take a look at some actual examples of elements, right? So in math, our elements will be numbers. So it says that a set is completely determined by what its elements are. And so let's say we have these numbers 1, 2, and 3. Are these a set? No, because they're not in set notation. So we have to first put it into the notation. And so how does our notation look like? If you remember, we have these brackets. So we have these brackets. And so now we have a set. This is set notation. And so it says that a set is completely determined by what its elements are. And so this is what determines the set. And here's one set. This is not a set. So if you have some numbers written out, that's not a set. It has to be in set notation form. Now it says not the order in which they might be listed. And so we could have the same set, but have it written out a whole different way. We could have it written out like this. Is that equivalent to our set right here? So we got set 1, set 2. Are they equivalent? Yes, they are. And it says which they might be listed. Not the order in which they might be listed, or the fact that some elements might be listed more than once. And so let's give it one more go for this. So let's say we have 1, 1, 2, 2, 3. What do you think about that? What do you think about this set? Well, if I take a look at the axiom, right? It's a true statement. Remember what an axiom is? A true statement. And so if I take a look at my axiom, I'll know that even though these numbers repeat, it's saying the same thing as this one and this set. So all these sets are equivalent to each other. So keep that in mind. Example 1a. Let a equals 1, 2, 3, b equals 3, 1, 2, and c equals 1, 1, 2, 3, 3, 3. And take note that these are all sets. So a equals the set of, so that's how you have to say it. A equals the set of 1, 2, 3, b equals the set of, so forth and so on. So if you're talking to someone, that's how you have to say it. The set of. I just said it that way so you guys could follow along. This is not that easy if you've never done this before. So the question's asking, what are the elements of A, B, and C? And so I'm going to give you guys about 15 seconds to think about what you think the elements are. And remember, I color coded it, so it won't be that hard. Alright, so if you guessed it, the elements are 1, 2, and 3. And what was our axiom saying? It says it doesn't matter how the elements are listed or if they repeat themselves. And so we only had 3 given elements here for these 3 sets. Alright, so how are A, B, and C related? So I'm going to give you 15 seconds to think about that. Alright, if you guessed it, they have the same elements, right? So really trivial question. Right? Trivial just means basic, easy. All you gotta say is they have the same elements. And so that's our answer. Really basic. Could be hard if you've never seen this before. B is the set of 0 equals 0. So let's take our time and think about this. So what does it mean to be a set? You guys remember it's a group of things, right? The elements, they're group of stuff within the set. And so let me draw a circle. And within the circle, we're going to have elements, right? In this case, we have the element 0. Does that make this 0 an element within this set? I'll give you a couple seconds to think about that. Well, it's not, because, and I'll explain it to you right now. So the set of 0 does not equal 0, and so that would be our answer. And I'll explain it to you right now. So the set of 0 does not equal 0 because the set of 0 is a set with one element. You heard me that? You heard me what I just said? It's a set of one element. So that's all that is. Namely 0. Whereas 0 is just the symbol that represents the number 0. So 0 is a symbol. As of any number, it's a symbol. While this is representing an element. So 2 different things. One's representing the symbol, one's representing an element within a set. And so we gotta take note of that. That we gotta define things by their definition. And in math, you always have to follow definitions. And this is the start of understanding what definitions are. And so let me write out the full answer. So this would probably give you half credit. You just put that. Because sometimes it's going to ask you why. It says, is this that? And you gotta explain yourself. And then it'll be like, explain. And so now I'm going to explain it to you. And it says, I'm going to repeat it one more time. It says, because the set of 0 is a set with one element. And that's what I just said right now, right? It's a set with one element. And it's pretty easy to tell that it has one element. Remember we've been learning about that right now, so if you don't know what an element is, you should rewatch the video again, because That's the very first thing that we mentioned. Alright, so it says 0 is a set with one element, namely 0. Okay, namely 0. And so that's just retelling you what what it means. It's just saying that it only has one element again. Whereas 0 is just a symbol. So I hope you guys understand what I'm trying to tell you. Because you got to take things by their definition in math. And you can't just say 2 equals 4. That's the equivalent of saying that. That's the best way I could explain it to you guys. You can't say 2 equals 4, and you can't say this, because that's the equivalent of saying something that doesn't make sense. And it doesn't make sense because we follow by the definition, right? By the axioms and all that good stuff I was talking about earlier. So let's complete this sentence. Whereas 0 is just a symbol that represents a number. So I hope you guys understand where I was coming from when I was saying this, because it's really important that the set of 0 does not equal 0, 2 doesn't equal 4, that's the same exact thing as saying 2 separate symbols means 2 different things. How many elements are in the set of 1, comma, and the set of 1? So we have a set within a set, and we'll learn about what that means later on. So we have a set within a set. So let's address this problem. We know what our elements are. Let's write them out. How many? It says how many elements are in the set. So we know we have 1 for sure. I hope you guys understand what I'm saying. We know we have 1 for sure. So we have this bracket. We know we have that. But what does this mean? Right? That's the question we need to be asking. Well, since this is a set, we need to take this as a set within the set. So that means we have 2 elements. And so let me explain it to you in math terms. It says 1 and the set whose only element is 1. So our answer is 1 and the, and the set. So what's our other element? It's another set whose only element is 1. And what does it mean to be a set? You have elements within it. So I hope you guys are understanding what's the process now. We have sets and we have elements. Really important. Whose only element, it's how I'll write element like this now, is 1. So that would be our answer. 1 and the set whose only element is 1. Or we could write this, probably a little faster. But if someone was to ask you to write it out like this versus symbolically, so this is symbolically and this is more of a, that means you wouldn't have to write regular elements. And this is more of a standard way of saying it, you know? And this is how you would say this. So this is how you would say this symbolically. You say 1 and the set whose only element is 1. So keep that in mind. And we learn a lot right now from this one problem. So D, for each non-negative integer n, let u of the subscript of n equal the subset of n comma negative n, find use of 1, use of 2, and use of 3. So let's take a look at this problem. What do we know? We know we have to use non-negative integers. And so that just means everything like this. 1, 2, 3, dot, dot. Remember what that is? Our ellipsis. And this is our set. So everything within this given set forward. So let's think. So that says integer n, let use of n equal the set of n comma negative n. So all we need to know is that everything's already given. So it says find use of 1. And so we just take a look right here and we know we're given the n's. So all we gotta do is plug them in. Pretty simple, huh? So use of 1, what's that equal to? If we just plug everything in, that means our set is 1 and minus 1. So you gotta understand what the question is asking. It says for each non-negative integer n, so that means for each of this is non-negative integers n, then we could plug numbers into our equation, which this is our equation slash function. And so that's all we're doing, but it already give us, so this is given. It give us without much thought of having to think about infinity and stuff. So we don't have to think about infinity because they already give us what we need to think about. So we already know that we only have 3 sets right here. And so let's see what this is. That's a set of 2 and negative 2. What's this say? 3? Pretty basic, huh? It looks all complicated at first, and then once you start getting the hang of it, it's pretty simple. And so when we're learning about discrete mathematics and how to approach it, we need to really be familiar with our definitions and our basic math, right? Because we need to know what our non-negative integers are, and we need to know that sometimes it gives us more than what we need to know. Sometimes questions give us more than what we need to know, so keep that in mind. Like this, we could have done without it, right? We could have just said, let use of n equals this, find this, rather than giving us this extra information, which we didn't really need. So keep that in mind. Certain sets of numbers are so frequently referred to that they are given special symbolic names. And so here's a chart of symbols and numbers that are so special that they have their own symbols. So let's see. Was this one, first one, have any guesses? It's a set of all real numbers. All real numbers. So that's really important. So let's take a look. I put a little chart down here. And so all real numbers comprises everything. Everything from irrational, rational integers, whole numbers, and natural numbers. Everything. And so the next one says Z. Set of all real integers. And so this could be a little confusing at first. So this is probably like 12 more stuff to remember. So this could get a little confusing. for R, we can remember R because R means real. And so now we gotta understand integers. So what can we know with mnemonics that can help us remember this? I could think zin. And so this is how I remember it. Zin. And you can remember this different ways, but just keep in mind you gotta remember what this means, because this will be coming up frequently in mathematics. And so this next one says Q, set of all real rational numbers. And so where does that fall between here? Rational numbers. Outside here. This is rational numbers. This is integers. And then real numbers out here. So we're getting closer to the middle. And so how do we remember this? Well, we know that the set of all real rational numbers is also known as the quotient of integers. So you know rational numbers are also known as quotients. And if you guys probably remember this, because this is something I remember when I was a little kid. Quotients. And so that's how you can remember rational. And it could be confusing. And so you could think of it in a different sense. So we could think of it as RQ, what follows after the alphabet. So it's A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R. QR. And so if you think about the alphabets, QR, Q to rational. So you could think of it like that. Alright, so N. And so what's N? N is natural numbers. This symbol is pretty important. It's a set of all positive integers. All positive integers. So it can't be a negative integer. And natural integers fall at the very beginning. So this is the fundamentals. And natural numbers, you could just think of it by the way it looks natural. This is the one we got to worry about the least, because in our textbook we're not going to use it as much. And this ends today's lecture, but this is the first part of this chapter and this section, and so there's going to be a part 2 of this and part 3, maybe part 2, I'm not sure yet. And if you guys like the video, please subscribe to my channel and give it a thumbs up, because I like making these videos and I like getting better at making these videos with you guys. And it helps a lot when I'm working 24 hours working on these videos. So thanks for everything, guys, and I can't wait to see you guys next time. Or girls guys. But thank you once again, and goodbye.